Hi, welcome back to Hi Jax Act 1. This is Lecture 3, Hi PyTrees. So this lecture is the third of 5 lectures in Act 1, which is all about the fundamental concepts that allow us to program with arrays in JAX. And the topic for today is to continue exploring our tour through sort of increasingly intricate neural networks. And today we'll be getting to implement multi-layer perceptron, which is actually the first neural network that you could call deep because it has neurons that are defined with their inputs coming from other neurons. Although it will end up being pretty shallow, as we'll see. In order to do this, we're going to be working with networks that have much more complex parameters than the simple 2 or 3 parameter models that we've worked with in the last few lectures. And that gives us a great chance to explore this fundamental JAX concept of PyTrees. And a PyTree is going to allow us to use the function transformations in the JAX transformation API using collections of vectors rather than individual vectors. And this is going to make it much easier to write code that works with a complex parameter with sort of multiple parts for a model like an MLP. And this is also just a chance to continue practicing other JAX array programming ideas, as we will see. So let's get straight into it. I'm here in the HiJax repository, and I'm going to cd into the lecture 03 directory, where we have this file MLP. And now MLP is the name multi-layer perceptron of the thing that we're going to be defining today. And this repository is currently set up with similar things as previously. I'm importing data classes now. As we'll see, this will help us define our own PyTrees. But we're not going to use that until a little bit later. We've got jax typing again. I don't think I mentioned it last time, but we have this PRNG key array type, which is the type that corresponds to a key for the random number generator. And then otherwise, we're just using arrays of floats and bools again. And later, we'll end up using this Python type itself as well. We're importing jax and jax numpy just like before. And we're also going to make use of inops this time. Just to make some of the data generation a little bit smoother. Otherwise, we've got a blank main function that we're going to start with. There's a few parameters added now. We have the number of points this time, but because we're not using the classical SGD algorithm, we'll be using minibatch SGD. We're separating the number of points from the number of steps. We've got a learning rate. We've got a number of hidden neurons that are going to be involved in our MLP, and we're going to initialize that to 256 by default. We can override that on the command line with Tyro if we want, like previously. And we have a mini batch size. This is how many data points the network is going to look at any one time. We'll fill in this main function in a minute, but just before we do, we've got essentially the same data and model visualization code as last time, which we will make use of shortly. So let's get started with the actual main function. And so the task is basically to create a data set. And I thought we should stick with the classification theme like last time, but instead of implementing a classifier for a linearly separable data set like last time, we're going to work with a data set that has a nonlinear decision boundary. And so the first step is going to be, well, I guess the first step we're going to need to do is initialize the random number generator. So we should do that. We'll have a key being the jax.random.key with our given seed. But now we need to initialize some training data. And so the idea is I want to generate a set of random points that have like classification labels, but I want them to be arranged in a nonlinear pattern or a pattern with a nonlinear decision boundary. And I'm basically going to make this like the classic XOR, exclusive OR data set, where we have sort of different corners of a square and one diagonal corresponds to the positive class and the other diagonal corresponds to the other class. And so let's see how we can go about doing this with JAX. So I'm going to need to fork my random number generator for all of my data generation. I'm going to do that by taking key data and key, and that's going to be the split of my initial key. And then I'm going to generate actually all of my data basically all at once. This time rather than generating it in pieces like last time, and just to show a different way to do it. We'll use jax.random.multivariate normal again. Multivariate normal. It's fine to just have these distributed as like Gaussian clouds. The key is going to be key data. This time I want the mean to be zeros. So I'm going to have 2D data again so that we can visualize it nice and easy. I'm okay with making the covariance matrix equal to 1 this time. In other words, equal to the identity, so the variance 1. It should be the 2 by 2 identity matrix. Now here, the shape. So I'm just going to generate all of my points all at once this time. I think last time I had this as a tuple. It doesn't matter if it's a tuple or a scalar integer here. It'll give us the same result. This will be a num points by 2 array. And so that will give us, in this case, the num points is 124 by default. So we can imagine this being 1024 by 2 array. And that's x's. And then, okay, what about y's? So y's is going to be our labels. And so last time I created 2 sets of labels and then moved them, I concatenated them just like with the data points. This time I'm going to generate all of the labels all together at once. And so in order to do that, I'm going to use inops because I think this is the easiest way to do it that I know of. So inops has various commands. We saw rearrange in the overture. We're going to use repeat today. And repeat is basically going to take an array and then stretch it out and repeat elements of the array. And the array that I want to repeat is a range 4. And so this is just the array, the JAX array 0, 1, 2, 3. These are going to be not the labels, but the 4 points in this, the 4 corners of this sort of square that I'm going to be drawing. And I want to basically make that, instead of an array of length n, in this case n is 4, I want to make it an array of n times k, or like n and k as the still one-dimensional. And I want to make k here num points over 4. And what that's going to do is, so 1024, for example, over 4 is 256. So this will make this an array of 256 copies of the first thing in this array, and then 256 copies of the next. So I'm going to have 256 zeros, and then 256 ones, and then so on, 2s and 3s, for a total of 1024 numbers here. So y's is going to be our array with that particular shape. Now, this is so far so good, but I haven't really generated the data yet. I need to do some more transformations. So I have 1 point cloud and 4 labels. I'm going to use these 4 labels. I guess I shouldn't necessarily call them y's. Let me change it up a little bit and call them c's. C's for corners. I'm going to use these corners in order to spread the data to these 4 different corners. And so one way to do that is to say I'm going to redefine x's as 0.5 times x's plus jnp dot array. I basically want to send each of these points to a different corner as the mean. So I'm going to be adding these vectors, and the points like distributed around the origin. So if I add a vector, then they'll become distributed around the point that I move them to. And so I'm going to have 4 different directions that I could send them in, either to -1, -1, or to -1, +1, or to actually let me do them in a different order. +1, +1. This will be the first diagonal, so this will be like -1, -1, +1, +1. And then the off diagonal, so -1 and +1 and +1, -1. And so I'm not going to add this vector actually. That will do some like broadcasting stuff. Yeah, this is right. I'm going to index into this with my c's variable. So this is going to mean that for each of the x's, if it's in the first 256, I'm going to index in with 0, and I'm going to get -1, -1. So I'll send the first 256 points of x's to this corner. And I'm scaling the vectors as well, is why I was okay using the covariance of 1 up here, because I'm going to set the standard deviation effectively to 1/2 instead of 1, and that will have the same effect. Anyway, so this should now spread out my x's in the way that I want. But I'm not quite done yet. I also need some labels. And so the labels, I want to use c's over 2. And so what that will do is that all of the corners that were 0 or 1 are going to get mapped to 0. And all of the corners that are 2 or 3 are going to get halved and rounded down to 1. And so this will now be effectively these labels. If I wanted, I could convert this to Boolean, but I think it's not going to matter. I'll just leave it as, by default, I suppose it would be an integer here. So now I have my data spread out. In order to, I guess I can visualize it now. So let me just see what we've done. So print vis data x's, y's, and let's make sure this has worked as intended. Oh yeah, I've got an issue here where something is not defined. Let me just type model equals none. This is just the type annotations. We're going to come back and fill that in later. And this is probably a typo. Yeah. Multivariate should be variate. Hopefully there's no more errors. Yeah, okay, here we go. So here's our data set. So I plotted this like last time on the -3 to -3 range on both the x0 and the x1, which are our 2 dimensions of our like inputs. And where before I generated basically a cloud here and a cloud here and called them 2 different classes, now I've had one big cloud and then I've scaled it and moved it to the 4 different corners, and I've used the corners 0 and 1, which were minus, or I guess 0 is here and 1 is here, -1, -1, and +1, +1, and then -1, +1 is up here, and +1, -1, they've been mapped to label 1. Yeah, that's right. So label 1 is cyan. So technically these are the positive examples, but yeah, that's not, that doesn't really matter. We've just got our 2 classes, and this is non-linearly separable. There's no single line you can put that will classify things. We're going to need to learn some non-linear decision boundaries, and MLPs can do that just fine, whereas the perceptron would famously not be able to represent a solution here. Okay, so what's the next step? So I guess this is still data, but it's still not shuffled, and so it would be nice to shuffle it. But actually, I guess it occurs to me that maybe we don't need to shuffle it because we'll be doing mini-batch gradient descent. We can like shuffle it later. The way I'm going to do mini-batches is I'm just going to pick random samples from this anyway, and it doesn't matter if I shuffle it and then pick random subsets or if I just pick random subsets from this array. So let's leave that as the data generation and move on to talking about our model and PyTrees. So here we go. So let's talk about PyTrees. So in order to initialize an MLP, we basically need to, we've done this a few times. We've initialized a model. We need 2 things to define a model. We need a parameter and we need a forward function, a function that represents the forward pass. And so for an MLP, there are many more parameters than before. Let me sort of draw what we are sort of thinking of when we say an MLP. And so I'll draw this on the whiteboard. Just let me refer to my notes for what I've called these different parameters. So I'm going to draw across the board what this MLP is going to be representing. We've got our 2 input nodes, which is a little bit like before we had, but I was drawing them going up the board last time. We're going to have an array of neurons in the middle, and this is the num hidden. These are the hidden neurons, and there's going to be 256 by default. But there's going to be a connection, a weighted connection, or I guess I can use green, weighted connection between each input and each of these 256 neurons. So that's 256 times 2. And then each of the neurons is also going to have a bias. And so that's another 256 parameters. I'm going to represent this here as W1, which is a 256 by 2 matrix, or maybe or its transpose, depending on your convention. And then this is going to be B1, which is going to be the bias for the first layer. Is going to be a vector of 256 that we're going to add to the activations of these neurons. That's only half of the forward pass, though, because we're going to have one more layer, and that's what makes it deep. The output neuron, which is the one that's going to make our logit for our prediction, is going to have connections from each of these hidden neurons. And so that's going to be another 256 connections. And so we'll call this W2. And it's a 256 by 1 matrix, or just 256 array. I guess that would be equivalent. And then we're also going to have a bias. And so this is going to be a scalar or a length 1 array, B2. And then that will give us enough, when we do all this calculation, each of these is like the perceptron. So each of these is going to scale the inputs by the weights on the edges coming in, add the bias, and then actually there'll be some nonlinearities in the center which allow it to do the nonlinear decision boundary. And then we'll be continuing to compute with those values as the input for the next neurons. And this is like a version of the perceptron that has 256 inputs instead of just 2. And then we're going to get a logit out. that will be our output, which we use, and we interpret that as like a probability or a log space probability that we're going to use for classification and to define our loss. So that's the idea. How do we turn that into code? Well, we're going to need at least a few like parameters. So far, when we've been defining parameters, we've been using a single floating point array to represent all the parameters. But that's going to become, and we've been unpacking it in the forward pass, that's going to become a little bit unwieldy. So let me just define a model instead as a tuple of parameters. And so I'm just going to define a type alias here to represent this. We're going to have our parameter involve 4 different arrays, one for each of these things that I've drawn up on the board. So the first is going to be a float array of shape 2 times hidden. And then the second is going to be a float array. This is W1. The second is going to be a float array of shape hidden. That's going to be B1, the biases of the hidden layer. And then we're going to have a float array of type hidden 1 transposed relative to the other one. The convention here is that this is the number of inputs and this is the number of outputs. So the inputs in the next layer transformation is hidden number of inputs and 1 output. And then of course we need our bias for the output layer as well, and that's just going to be of length 1, which I could use a scalar here, but this is more general. Okay, so now this tuple is going to represent a single parameter, and we'll figure out later how to take a gradient with respect to all of these arrays rather than just any one of them. The JAX API is going to make that really easy. But now we could define, before we initialize, I guess we could define the forward pass to take W of type model, and then maybe an X. Let's do a batch of inputs all at once, because we're going to need to do mini batches later. And so we'll say this is batch size multiplied by 2, because that's the dimension of our inputs. And the output here should be a single floating point logit. So we'll make, oh, actually, that's wrong. Sorry, because we have a batch, it will be a batch of these logits. So it'll be batch size, and I better straighten out the code here. So so we have first argument being this sort of tuple, and the second argument is going to be the batch of data, and then the output is going to be a batch of logits, of outputs. And so now let's actually implement this forward pass. So how to implement the forward pass? Oh, I'm just looking at my notes and I'm noticing that I made it so that the forward pass actually outputs the batch dimension and also this 1. I think it doesn't really matter, but I'm just going to use that convention. So we have our W, it's a tuple, so we can unpack it to get our matrices W1, our vector B1, our matrix W2, and our vector B2, all come from this W. This is just a tuple, and so this is just unpacking like normal Python. There's nothing JAX specific about that. Now we're going to implement the first layer, layer 1. And so this is going to, we can use, I guess we should call these X's because it's a batch. That's what I have in my solution as well. We should call this X's, and we're going to overwrite that by sort of calculating the outputs of the first layer. And we said that to do that, we should take X's and do a matrix multiplication. So all of the rows of this is batch size by 2, and then we're going to multiply it by a 2 by hidden matrix, and that should give us a batch size by hidden. And so there'll be 1 row for each example, and then there'll be hidden values in the row representing the activations of all of these neurons. And so that is going to be that. And then we need to plus the biases to those. Now this is already a hidden vector, and so that's the right shape to add to this. And then we've done the layer transformation. The next step is to do the nonlinearity activation, as it's called. And let's just use ReLU. So we'll overwrite this with jax.nn.ReLU. So jax.nn is a collection of functions that are useful for defining neural networks, and ReLU is one of them. But I'm sure you've seen ReLU before. This is just the rectified linear unit. It's really just the maximum. It's just the positive part of the value. So all of the negative values get set to 0, and all the positive ones stay. And so we'll take X's, and this will be a sufficient nonlinearity for our uses today. And so now let's define layer 2 transformation. And so this is going to be, the output of this layer is going to be just the single logits thing. So we'll call it logits equals X's multiplied by W2 and plus B2 again. And so let's just check the shapes here. We previously had that this was a batch size by hidden. We took the ReLU, which is going to act element-wise, so this is still going to be batch size by hidden. And now we've got batch size by hidden times hidden by 1. And so we should have batch size by 1. We're adding a 1 to that. That's going to broadcast over the batch, and we'll be adding the bias to all of the outputs. And then we'll have, in the end, batch size by 1, which is what we were hoping to return. So I think we can just go ahead and return logits. And so that is going to be the forward pass. Now, the only thing to note about this regarding PyTrees is, yes, here we have this model coming in as a tuple, and we've unpacked the vectors. This is much easier than if you imagine if in jax you had to come up with some encoding where the bias was like, well, let's say the first however many entries of your array corresponded to W1, and you would use a slice to take those out. And then the next few entries correspond to the bias one, and then the next few entries correspond to this and that. This allows us to just sort of use Python data structures to organize ourselves. And actually, it's not just tuples. PyTrees refers to basically any standard Python container plus extra containers that you can define yourself. And basically what we have is this could even be a dictionary, and the values would be the values, and then we're going to be able to treat that as a collection of vectors that is collected in some specific way. In this case, where you have a dictionary where the keys represent the sort of different children, and then the values represent the leaves of the tree. This is the actual vectors. As long as you have arrays, jax arrays, not numpy arrays, jax arrays at the leaves of any recursive structure, a tuple of tuple, a list of lists, a dictionary of dictionaries of tuples of lists, whatever. Jax can basically handle that all the same, and such a collection is called a PyTree. And so that is good. Now our next step is to actually initialize this. And so it's going to be a little bit tricky to initialize it, because I guess we're going to have to initialize each of these individually and then pack them into a tuple. So we need to make sure that we're conforming to this shape when we actually create a W or a weight vector. So let's do that now. So let's initialize the model. And so we're going to need a key model init to fork that of our random number generator with split. And then how did I do this? Okay, so yeah, I think there's maybe like other ways to do this, but one way you could do it is you could just separately initialize all of these elements and then pack them into a tuple. So we could create W1 as a jax.random.normal. This is just going to individually set the parameters of jax. Of a thing that we asked the shape for. So we can use the key model init. Actually, you know what? Instead of using key model init, what I'm going to do is show you a practice that I sometimes use when I'm managing the state of my random number generator. And that's to split the key in a way that corresponds to different conceptual sections of the code. Basically, what I would like is that the key that comes out of this section and gets used for the training loop shouldn't depend on how many times we split the key in order to initialize the model. And so what I'm going to do is I'm going to split this again. I'm going to say key W1 key model init is equal to jax.random.split key model init. And so that is going to mean that within this part of the random number generator state tree, I'm going to have another fork, and that I'm going to use to get the different parts of the random number state that I'm going to use for initializing the different parts of the model. The first of which is going to be W1. So let's, instead of using key model init, let's use key W1 here. And then we just need to know what is the shape of this standard normal data that we want. And the shape is going to be 2. We decided that our shape was 2 times hidden. And so we've got hidden as a num hidden here as an input to our main function. And so let's say this can be 2 times num hidden as the shape that we request. And that is going to initialize standard normal random entries in this W1 matrix. It's common to initialize the biases actually not randomly at all. So we use jnp.zeros for this. We can just initialize them to 0, and then that's fine. I mean, it's also common to use different initialization schemes for the matrix, but this one is just simple. We're just going to do this for today. And so we don't need to fork the random number generator. What size do we need? We need num hidden, because that's how many biases we need in the first layer. How about W2? So W2 is going to be very similar to this. I'm going to, in fact, copy this code and just rewrite it with W2. I might just replace W1 with W2, make sure there's no double entries of that. And then, so we've got key W2, key model init. So again, we're splitting this model init key, and that means that this W1 and W2 are both branches off this initial split. And if we had maybe like extra layers, W3, W4, it wouldn't change the key that eventually gets starting the training loop. And so all of the random batches that we then draw downstream of the key that starts the training loop would be the same no matter if we make a change to the model. And that's just an extra sort of layer of modularity in the determinism that we have. So it's a good practice. So this is W2. The last thing we need is bias2. So bias2 is just going to be jnp.zeros, and this needs to be just length 1. That's what we need for that. And so now we've got W1, B1, W2, and B2. We're ready to initialize W, lowercase w, which is our weight vector, or like our parameter generally, and it's going to be a PyTree, which means it's just going to be a tuple. There's no extra work that we need to do here to make JAX be able to handle this. It will just understand tuples. If you even wanted, you could make this a list of layers or something like that, and each layer could be a tuple. If you wanted to sort of have some other structure to your network, that would be totally fine as well. But we just need to decide something and then stick with it. So we're going to go with this tuple for now. Okay, so we've initialized the model. I think it would be nice if we could visualize the model to see if we've done everything correctly at this point. So let's do that. Let's just use this visModel function, which takes W, X's, and Y's as input, and also a step like we have previously. I'm going to use -1 this time because I know that it's going to add 1 to the step, and we haven't done any steps yet. And we'll see if I've made any mistakes. Okay, yes, it looks like I have made a mistake here. And let me just check to see what that is. This is coming from the forward pass when I use this matrix multiplication here. So this is one of those issues that comes up with batching, and I'm excited to get rid of, to learn about VMAP and then never have to write batched code again. But for today, we haven't looked in detail at VMAP yet. That's coming in a future lecture. So let's just take a close look at what's going on here, at the shapes involved. So it's saying that we require contracting dimensions to have the same shape, whereas we got 256 and 2. Let me look at the cheat sheet to see. I thought this was fine. It may be that I've just initialized something wrong. Oh yeah, of course. I remember. I copied too much code. This is not actually an issue with the matrix multiplication. It's here. This shape is supposed to be num hidden 1. It was getting 2 instead of 256. I guess I should learn not to copy code and just type it all out and make the changes that we need to make. So of course the shape of W2, some of you probably caught this, the shape was meant to be num hidden 1. We decided that earlier. So now this should probably work, hopefully. Yeah, there we go. Okay, so we can see that when we randomly initialize, this visualization is a little bit different from what we've had in the past, where we had like a white line representing the decision boundary. Because this decision boundary is nonlinear, I thought the easiest way to represent this would be to basically sample the function at all of the points and use that to color the output underneath the points. And so you can see that it's actually initially predicting a decision boundary that just happens to look like this, which is nonlinear already, but it's not the correct decision boundary. I mean, it's classifying all of these points here as in the blue class, in the cyan class, in the positive class. It's getting these ones right, but it's getting all of these ones wrong and, some of these ones right. So we're going to have to learn to move these lines in the decision boundary until we get the shape that we're after. I will note that the color scale here, so that we can see both the points and also the background, I've kind of desaturated the background. So this sort of dark grayed out cyan color represents like maximally predicting cyan. And this color in the back represents maximally predicting magenta. Okay, so that's visualized the model, and we're ready to start training. And so here's where we're going to learn some more about what you need to do to make JAX work with PyTrees. So far, so good. We've just defined a tuple. Like, anyone can do that. We could have done that previously. The trick is going to be when it comes to taking and then calculating and then applying gradients, that we're going to need to be able to manage this tuple. And fortunately, JAX makes that really easy, but we need to just see how to do it. So, okay. So let's get started. And like I said, I'm going to take a key for the training loop and separate that from anything, so that if I did want to do anything other than training after this in the function, I would have this key to start fresh, and it wouldn't matter how many times I've been around the training loop, for example. So let's just jax.random.split here, this key, and then we're going to go on our loop. So for time step in range num steps, which is our argument that we have from the main function, we're going to, first we need to sample a random mini batch. And then we need to actually do a gradient step. So how are we going to sample this mini batch? This is going to be an instance of using jax random choice, another jax random function that we haven't met yet. Let me just, as good practice, I mean, this is, I think, the only randomness that I'm going to use in the iteration, so I could just use key train. But let me, sorry, I could just, no, I need, sorry, let me take that back. I need to split off a key for this iteration, because I'm going to need key to go forward into the next iteration, or key train, that is. So key mini batch, key train is going to be jax random split of key train. And then every time I go around this loop, it's going to overwrite key train. And that is how I'm going to manage. So, you know, this is going to end up being a very deep tree after I've done however many steps. I requested like 500 or something. This is going to, end up taking a while. This is going to end up taking a lot of forks of the random number. But you can see that because we're overriding, it's going to take the latest one in each iteration, because we're overriding this value. And then, like I was saying, at the end of the loop, we'll still have this key. And it doesn't matter how many times we fork to key train, key will be ready to go to deterministically do whatever we need next, which in this case is nothing, but that's okay. So anyway, on to actually selecting the mini batch. So the mini batch itself is going to be, I guess I should first say I'm going to want like a set of indices. The mini batch indices are going to be given from jax random choice. And I want to do, jax random choice can also like subsample an array directly, but I want to subsample two different arrays with the same indices, because I have my x's for the data inputs and the y's for the data labels. So I want both of those things to choose the same, I want to choose the same rows from both. So I'm going to just get the indices, and then I'm going to use this set of random indices to go into both arrays. And so the key will be our key mini batch. And then A is going to be the array that you want to subsample. But in this case, I'm just going to use num points. Actually, it shouldn't be num points. That's wrong. It should be batch size, right? I think that might be a typo in my solution. Let me just double check what we called it here. Mini batch size, actually. So let's choose mini batch size. I think that's a typo in my solution, where I use num points there instead, which would be full batch gradient descent. But we're doing mini batch gradient descent. So, oh no, that's wrong. I was wrong. So it is supposed to be num points. So so A is the array to subsample. So not the shape. So num points is not the array to subsample, but it's the size of an array we'd like to subsample indices for. So this is a shortcut for putting in a range, JNP a range num points. And it's going to subsample indices between 0 and 1023. And this is right, because we do want to consider all the possible indices of our data. And then where I was getting confused is that the next thing we want to do is say the shape should be the mini batch size. Not the number of points. And so this should give us back a vector of mini batch size points subsampled from num points. And I think I can say replace equals false to make sure that there's no duplicates. Although this is not essential for training, I guess it would be fine. There's nothing like in principle wrong with having duplicates, although it's common to actually, rather than sampling like this, it's common to shuffle the array and then like read through it once at a time to ensure that you're getting each of the data points an even number of times. But just for simplicity, let's do it this way. And then the actual batch itself, x mini batch, x's batch is going to be equal to x's mini batch IDs, and then the y's for the batch are going to be the same, y's mini batch IDX. Okay, so we've sampled the mini batch. Now we can do a gradient step, and so now we finally have to handle this tuple parameter that we have. And you'll be pleased to know that in order to do so, we actually don't really have to do anything differently, at least to calculate the gradients, although applying them, as we'll see in the next step, is going to be a little bit of an extra step. But value and grad is fully capable of taking the derivative of a loss function with respect to the first argument, where the first argument is a tuple, because it can handle any PyTree, and a tuple is just a PyTree. And so, in other words, it can handle any nested collection of Python containers, trees, tuples, lists, dictionaries, and some custom ones that we can define ourselves, like we'll do later. And so nothing has to change here. We just have to pass in the data to our loss function. We haven't defined the loss function yet, but we'll do that in a moment. Let's go ahead and define the loss function, and then we'll see how to apply these gradients. But first, the loss function. So this is going to be a very similar loss function to last time. We're going to be using cross entropy. However, instead of handling one example at a time, like last time, we're handling a mini batch. So that's going to make it that we need to take the average cross entropy, where the cross entropies are calculated for each example. And so let's define this loss function. So this is going to be, it's going to take our model as input. And this is just a PyTree, and this is the first argument, so this is what we're taking the derivative with respect to when we do autograd. And then the x's is going to be our float array of inputs, batch size by 2, and then the y's is going to be our bool array. I don't think I actually made them booleans, so there's actually going to be an int array, but I don't know if I said these annotations we're not checking these anywhere. These are just for our convenience and readability. So this is actually an example where the labels are going to mismatch the code, and they'll be kind of worse than no annotations or something like that. So I'm sorry for that. But anyway, we have a float as output, which is our total average cross entropy. And so actually calculating the cross entropies is going to be similar to last time. We're going to want to use our forward pass to get the logits for the batch. Forward of w and x's, and this will give us a batch of outputs. Remember that we had this convention. Actually, I think it was maybe a bad convention now that I think of it, but all of the visualization code is written with this convention in mind already. We have this convention that the output is of shape batch size by 1. And really what I want is really just scalars here. So I'm going to subsample the 0th dimension, the 0th index along the 2nd dimension, and that is going to give us turn that 1 into nothing. So this is now going to be a float batch size array. And then I've got my logits. So now I want to calculate the cross entropies, and we use the same formula as last time. But for a batch, cross entropies is going to be equal to jnp.log add exp of 0 and logits minus y's times logits. And it just so happens that this is basically the same code as last time, but with plurals instead of singular logit and y's, and it's just going to work fine because of the broadcasting. But this will give us now a vector of batch size cross entropy values, and we want to take the mean. So mean, actually we're just going to directly return this, so I can just return jnp.mean of cross entropies. And so this will compute the average of these and then return it. So that is easy. Now we've got the loss. Now we're taking the gradient with respect to that. We're getting the value and grad with this jax transformation. And I've told you it handles the fact that this is a tuple just completely transparently. It will give us back a tuple, in fact, of gradients, where it will have the same shape as the PyTree we gave in. So it's going to be a model, actually, basically a model tuple where we're going to have a float of the gradient with the output with respect to each of the 2 times hidden parameters in here. And then the second entry will be a vector of gradients. And then the third entry will be hidden by 1, and so on. And so what we have now is basically 2 tuples. We have the model tuple W and we have the gradient tuple. And we have to, for each of the entries in the tuple, apply this gradients to get the entries in the new tuple. Now, one way you could do this is you could say, let me define a new W1, and that is going to be the old W0, which is going to be our W1, minus the learning rate times G0, and then the new W2, or I guess I should do B1 next, is going to be W1 minus, and so on. But notice that we're going to be basically applying the same operation of each on each element, on each leaf of the, in general, of the PyTree. In this case, in each entry in the tuple. And JAX has a utility that will allow us to do this. This is called a mapping operation. And if we're mapping over a PyTree, we're going to be able to use a JAX utility to do this. So we're going to use jax.tree.map. And we're going to say the new W is equal to jax.tree.map, where the input to this mapping function is going to be the function that we're applying at each leaf, and the other inputs are going to be the PyTrees that we want to map over. So this will be lambda. We're going to have a leaf coming from the model and a leaf coming from the grad, so grad leaf. And then for each pair of these, we're going to want to say that the new thing is the model leaf minus the learning rate times the grad leaf. And I'm not sure how to wrap a lambda function, but maybe we can just do this to make sure it all fits on one line. And then so that will be the function that we're mapping, and then we need to map over some PyTree, and so the PyTree we're mapping over will be W, and then we also need to map over G so that we have the gradients corresponding to this. And this will be basically like doing a zip of these PyTrees, and then we get all of the corresponding pairs of leaves, and we apply this calculation to combine them to get the new value of the leaf, and that comes into the output, which we're then using to override the model. So that is the JAX way of applying gradients to a PyTree. And it saves a little, well, actually, I mean, the number of lines is like similar to if we were to do this sort of one by one for this model. But for more complex models, this is going to save a lot of hassle. And it also means that this code would work no matter what PyTree we gave in. Even if we sort of changed it later, we wouldn't have to change this code. And so that is how we calculate gradients of models. And so with that, I think we're nearly done. So we're ready to get this thing training. And so let me just visualize it. So we want to, like before, we want to compute a plot where the plot is going to be from our Viz model. And Viz model takes W, X's, and Y's, and the step number. And so I can actually use T as the step number now because I'm inside the loop. And it's going to add 1 to it like last time to sort of make sure that this represents the number of steps we've been through by this point, because we're at the end of the step. And then I'm going to do my tricky print thing again, where I print the, I use matplotlib to print the negative of the plot, which is going to scrub that many rows of the height of the plot, and then the plot. And because all the plots are the same size, this should create a nice animation, especially if I pair it with time.sleep 0.02 like before. So we get roughly 50 frames a second plus the time that it takes to actually do the steps, which is pretty quick in this case. And then I think we're ready to run the code. Let's see if there are any bugs. Yeah, okay, so there's some issue. Okay, so I thought I could put in a shape of minibatch size here. I'm just looking at this thing, and I've got shape argument of JAX random choice must be a sequence, got 64, the scalar. So that's not right. I need to, I thought I could get away with it, but I need to give a tuple where the first entry of the tuple is minibatch size, and so that it's actually a sequence. Equivalently, you could do a list here, I guess. But I don't know, I just normally prefer tuples to lists if they're not going to change in size. Okay, so now we're training. Look, and it's a nonlinear decision boundary. It's actually pretty quickly found that the boundary should kind of exclude parts of the data. It it's a little bit unstable, and I'm worried that I might have missed something compared to what I was expecting, but it does manage to basically find a good decision boundary where it's kind of classifying all of these cyan points as cyan, all of these cyan points as cyan, and all of the remaining points as magenta in a clearly very non-linear way. Let's run that again just so we can see it one more time. It sort of very quickly finds this, this decision boundary and then sort of hops around using the stochasticity and the mini-batches. So there we go. Now, I am slightly worried that this is a lot more unstable than I was anticipating. So I'm just going to double check my solution to see if I can spot if I missed anything. But it might just be the case that this is just not as stable as or like I'm misremembering how stable it was. No, actually, this looks, I guess, roughly as stable as what I had in my solution. So, okay, this must be it. So anyway, there we go. We have very quickly found a solution to this problem, and it's a nonlinear decision boundary. So well done, the MLP. It's triumphantly learned this data set. So now the last thing that I wanted to talk about is that instead of using tuples for our PyTrees, you'll often want to use something more kind of structured and descriptive, because it's a little bit annoying that, for example, in this forward pass, we had to sort of do this unpacking, and if we change the structure of the PyTree, that's like maybe going to be a little bit annoying. So what I want to do instead is basically completely get rid of this code, but I'll just comment it out for sort of posterity, and say I want to create a class to be my model. I want my model to be a data class, in fact. So let me define a class model, and I want this to have parameters that I can index with their names. So like I want this to be W1, and I want this to be B1, so that I can just do model.W1 to get the weight vector. And then you can also have like nested structure very easily here by composing classes. And so W2 is this one, and then B2, and then I got to get rid of these commas. And then this model is also giving me, I got to make this data class, sorry. So we've imported data classes. So that should do it. And then my forward method, my forward function can actually become a method. And so I can just put that as a part of this class. Just for posterity again, I'm going to keep this up here and just comment it out. And I'm going to use a copy of it as the method. So we can just indent this and then uncomment it, and then say this is now, this W is going to be a model. This is where we need the self type annotation, because model is in the process of being defined. And it would be more traditional to call this self for a method. And so then I can go through, and instead of unpacking this like it's a tuple, I just want to go through and I want to say where I'm using W1, I want to do self.W1 and self.B1 and self.W2 and self.B2. And then this will be basically the same as before, but it's prepared to sort of be a more scalable way of implementing this. And if you wanted, you could actually also take the code that we use to initialize the model and say that's kind of also specific to the model, and we could use this as an alternative constructor. And so why don't I just comment this out too, and then take the code and move it up here and make it another method that is going to be on this class and is going to return a fresh parameter, so that anytime I need a parameter, I don't have to remember exactly the details of the structure. I can have that all encapsulated nicely in this class. And so I'm going to create this init function. So I want this actually to be a static method. I want to be able to call capital M model.init and give like some sizes or something like that. And it should be able to give me back a fresh instance. And so let's make this a static method. The input that I do need is the key. So that's where we need this prng key array, which is the type of our random number state. And then the return value here should actually be self. And so the return value is going to be self. Oh, also I guess I need this num hidden, which is the parameter here. So let's do num hidden, which is going to be an integer. And so now I'm ready to uncomment this and basically use this to turn this into the code for an initialization. So instead of key model init, I can actually I'm free to rename this. I could call this parameter key model init, but why don't I just call it key to be sort of simpler? And it's sort of the only key, it's the main key that we're sort of threading through the rest of this computation. So instead of key model init, I'll just call it key. And then I'm still splitting off key w1 and using that, and then splitting off key w2 and then using that, and then this key goes unused because we have no more randomness in the function. And anyway, I've built this w1, b1, w2, b2, and in order to actually create the object, instead of this w, I need to use the actual sort of built-in constructor of this thing. So that'll be model w1 equals this, b1 equals this, w2 equals this, and b2 equals this. And then that is going to be my w, and I can actually return that because that is what I want to be the output of this function, this sort of self representing an actual model. So this static method means that I can now, in my code, I can go ahead and I can say w is equal to model.init, and then I can pass in my key model init, and I can pass in the num hidden as my hyperparameter here. And this should now still work. However, I guess I'm going to need to, everywhere I had the forward pass, I'm going to switch to using the forward method. So let me just keep that code there and switch to w.forward x's instead of forward w x's. And then I think there are some more places in the visualization code where I do the same thing. And that is, I've already prepared the code that I just need to swap to the other version that uses w forward x's instead of forward w x's. Is that all? I think that's all. So that's all of the instances of forward. And so this should, unless I missed something, this should still train. Okay, I've obviously missed something. This is a very long... oh yeah, of course. So yeah, this is actually, I was hoping to get this error. So this is a very long output. It's actually printing out the entirety of the data class. So we've got type error. When we go to take the value and grad loss of this function, it notices that the argument that we give it, this w that we give it, is a model data class instead of a tuple. Before it was a tuple, now it's a model data class. And it's going to say that this argument, this model, which then has all these randomly initialized parameters, and there's a lot of them. There's the w1, and then here's b1. It's this big array of zeros. Remember, we zero initialized that. And then w2 is a num hidden array. There's a whole bunch more. And then b2 is just the scalar 0. But anyway, that argument is of type class main model, which is not a valid jax type. In other words, not a valid PyTree. And that's because we missed one step, or I missed one step, which is that once you have the data class, you have to register it as a PyTree. You have to basically tell Jax, this is a class that I've custom defined that you should, all your API functions should accept and treat just like any other nested collection of data. And that is going to be the final step. And to do that, it's very easy. We use jax.tree util.register data class. And it's a decorator of the class, just like the data class decorator itself. So this defines a model, this redefines it as a data class, and this redefines that data class as the same data class, but tells Jax about it, so that Jax knows to expect it. And now we should see, unless there's other errors, we should see this training working as expected, as intended. There we go. So this is now training with a custom model represented with this data class code, which is going to be much more modular, and this is how we'll build bigger, more complex neural networks in the future with sort of nested components. Yeah, I think that's it for the demo. So let me just flick through the code one more time. And in summary, we've sort of, we generated some slightly more complex data. That didn't really have much to do with PyTrees. But then we got to actually initializing our model, and we defined our model as first a tuple and then later as a data class with different components. And then we initialized each of the components using this, what eventually became this init method. And then in the training, we were doing mini-batch gradient descent this time, so we had to randomly pick a mini-batch, a subsample of the data set to train on. And then we do gradient steps. And when it came to doing the gradient steps, calculating the gradients was just as easy as before because Jax is already set up to work with PyTrees in the API. And we're going to see this later. It's also going to work with PyTrees when it comes to VMAP. It's going to work with PyTrees when it comes to do any of the sort of Jax operations on functions. Their arguments can be like Jax arrays, or they can be PyTrees of Jax arrays. It was a little bit more complicated to do the update. If we wanted, I guess we could define a method that does this update and internally does the map. But this is going to work with any model, no matter what it is. So it's not like we have to change this code if we change the model. So this is already pretty sensible to do it this way. And learning jax.tree.map was sort of the first use of this jax.tree library. And I'll go ahead and show you that when it comes to PyTrees, you can read more about them in the Jax documentation, but you might like to check out the list of functions that's available in the jax.tree module. We've got the kind of things you would expect, like map, reduce. There's a couple of other ones that are a little bit more obscure, like structure and transpose and leaves, which kind of... Well, actually, leaves is pretty simple. It just turns it just walks the PyTree and turns it into basically a tuple of all of the leaves. I'm not sure if it's exactly a tuple or maybe just like an iterator or something, but anyway. Flatten, I guess, is sort of similar. You can, but then there's other things with like PyTrees of PyTrees, so that's what transpose corresponds to. And structures is like a specification of the PyTree with no actual values. You can imagine it's like the tree structure itself, but then rather than an example of the tree structure where you actually have the tree structure and then it actually contains leaves, which is useful in some cases, but not that useful. What's another one? So all is another one that you might expect. This is going to go through all of the leaves of the PyTree and turn them into Boolean leaves where if all of the methods are true. So this is basically mapping all over the PyTree, and so that is useful. Is it all, or is it maybe also reducing? Let's check it out. So the return is just a single Boolean. So this must be mapping and reducing. So that's nice. It does both those steps in once for us if you need that. Another library to look at is the jax.tree util module. And so the jax.tree module is actually basically has a bunch of aliases for some commonly used functions from this module. So you'll see all show up again, and yeah, here's tree all, tree map, tree reduce. These are actually the same as the tree versions. But then there's a bunch of other functions here that are useful for doing slightly different things, working with key definitions and registering PyTrees with the Jax API. So what we used was register data class. And so there are some other custom kind of fields here that you can use to customize how the data class is registered with the Jax API in terms of which fields of the data class do you want to designate as your like actual leaf nodes, and which of them are maybe just other structural information. And so we'll have course to use this from time to time as well. Anyway, there's much more information in the docs if you want to have a read. I think that's all for now, so it only remains for me to leave you with a challenge. And so I'll leave you with the following challenge. So if we head back up to the top of our script here where we had a model that had 2 layers, which we remember from the whiteboard. Sorry about the glare. But MLPs is sort of a broad term that also encompasses much deeper structures where there's multiple layers nested into each other. And what I'd like you to do is try to adapt this model data class to have more layers, as many as you can sort of be bothered to type, and then we'll sort of run in good time on whatever laptop you're using and see if it makes any difference to the training if you nest a whole bunch of more layers together. And so I guess you can have some fun with that, and it's up to you exactly what type of architecture to target, but maybe adding at least one more layer and then as many more layers as you have ambition for. And so I'll leave it there, and I'll see you in the next lecture. Bye.